This is a short tutorial on balancing chemical equations. Balancing of chemical equations relies on a fundamental law of chemistry, which is the law of conservation of matter. Conservation of matter states that matter in the form of atoms, can neither be created or destroyed during a chemical reaction. Of course, during nuclear reactions, we can destroy matter. The core of the law tells us that every atom on one side of a chemical equation must appear on the other side. It should be noted that laws like this are established empirically, which means in the laboratory, and are not a theory based on fundamental understandings of the universe. Well, how is this law of conservation of matter related to the conservation of energy, which we've already discussed? Well, if you talk to a physicist, physicists will tell you that energy and matter are the same thing, and they are interchangeable through the formula E equals mc squared. Yes, that's Albert Einstein. And what that means is, as soon as we understand that either energy or matter is conserved, that the other must be conserved too, unless we go through this interchange process. And if we total the energy and mass up in a system, they have to be constant during the course of our experiments. Well, we need to understand that the chemical equations that we're learning to write, represent chemical reactions. So we're going to use chemical formulas that represent physical molecules. If we take a look at a molecule like glucose, which has the molecular formula of C6H12O6, we can draw a chemical structure like the one shown here in Lewis structure form to give us an idea of exactly how the atoms in that molecule are distributed. When we're writing chemical equations, an arrow is used to separate reactants, which will be on the left side of our equation, from the products, which will be shown on the right side of our equation. In some chemical reactions, we'll also show phase information, whether the material we're using is in the form of a solid, liquid, a gas, or in solution. It should be noted that in balanced chemical equations, there's no information about the reaction rate, which will be addressed in future lectures on kinetics. Chemical reactions can be written in either direction, and changing the direction, changing which direction the arrow points in, redefines what we're defining as a reactant and a product. Well, balancing chemical equations, since it's the law, we have to learn how to do it properly. So let's go ahead and take a look at some examples of balancing chemical equations. We'll start out initially with some easy ones and work our way towards harder ones. Let's first look at the reaction between solid calcium and gaseous oxygen to form calcium oxide. To balance this chemical equation, we're going to have to count up each individual element's atoms on both sides of the equation and make sure that the numbers agree with each other. Well, clearly, we're starting out with one calcium atom and two oxygen atoms as reactants. Our product has one calcium atom, we're certainly okay there, but only one oxygen atom. Well, our chemical equation is not balanced. We have two atoms of oxygen on one side. We have one atom of oxygen on the other. Well, we're going to address that problem by putting a stoichiometric coefficient of 2 in front of calcium oxide, indicating that we're going to create two molecules of calcium oxide. That now gives me two atoms of calcium and two atoms of oxygen. My oxygen atoms now agree with each other, but my calcium atoms do not. I am also going to have to stick a 2 as a stoichiometric coefficient in front of calcium. That now gives me two calciums, two oxygens on the left-hand side, two calciums, two oxygens on the right-hand side. So my chemical equation is balanced. Let's look at a slightly more complex reaction where we're going to start out with solid iron, react that with gaseous oxygen to give us iron oxide, Fe2O3. It should be noted there are various formulas for iron oxide that depend on what the oxidation state of iron is in the compound. Well, if we go ahead and count up atoms, clearly we have one atom of iron and two atoms of oxygen on the left-hand side. On the right-hand side for our products, we have two atoms of iron and three atoms of oxygen, so the equation is clearly not balanced. In looking at reactants and products, one of the things that should leap out at us is that on the reactant side, oxygen comes in units of 2. On the product side, oxygen comes in units of 3. So it's going to be a challenge to balance out this set of formulas. Well, we're going to do it by putting a stoichiometric coefficient of 2 in front of my iron oxide. That's going to give me four iron atoms and 6 oxygen atoms. Well, 6 is divisible by 2. If I divide 6 by 2, as in O2, I'm going to get 3 oxygen atoms. Those 3 oxygen atoms, three oxygen molecules, O2, are going to give me 6 oxygen atoms. I now have a stoichiometric coefficient of 4 in front of the iron, 3 in front of the oxygen, giving me 4 iron reactant atoms, 6 oxygen reactant atoms. And my products are 4 iron atoms and 6 oxygen atoms, so I'm balanced. Well, let's take a look at a similar reaction where we're going to react iron with chlorine gas rather than gaseous oxygen to give us in solution, aqueous solution, iron chloride. Well, again, if I count up my reactants, I have 1 iron atom, I have 2 chlorine atoms. On the product side, I have 1 iron atom, I'm good there, but I have 3 chlorine atoms instead of 2. Well, again, we should notice that on the reactant side, chlorine comes in units of 2. On the product side, chlorine comes in units of 3. The only way we're going to make those balance out is by ending up with 6 chlorine atoms on each side of the reaction arrow. So I'm going to multiply my products by a stoichiometric coefficient of 2. That will give me 2 irons and 6 chlorines. I'm going to then multiply my iron reactant by 2 to give me 2 iron atoms. And then finally, if I need 6 chlorine atoms and they come in units of 2, Cl2, I'm going to have to multiply my chlorine gas by 3. That will give me 6 chlorine atoms total. And now I have a balanced chemical equation. Let's take a look at one more complex reaction where I'm starting out with a complex large carbon molecule, which is stearic acid. Stearic acid has 18 carbons, 36 hydrogens, and 2 oxygens. When I oxidize stearic acid, whether I do it metabolically in a biological system or on the lab bench by burning it, I'm going to get carbon dioxide and water as products. Well, let's go ahead and try to balance this. On the left-hand side, I have 18 carbon atoms and I have 36 hydrogen atoms. In stearic acid, I also have 2 oxygen atoms. And of course, for O2, I have 2 oxygen atoms. On carbon dioxide has 1 carbon, 2 oxygens, water, 2 hydrogens, and 1 oxygen. Now, as we think about a strategy to balance this chemical equation, we should note that every time we change the number of stearic acid molecules, we simultaneously change carbon, hydrogen, and oxygen. On the other hand, if we change the stoichiometric coefficient for O2, the only element we're affecting is oxygen. When we have a situation like this, we should leave the independent element, in this case oxygen, for last. So let's start out by balancing carbon. Well, if I have 18 carbons on the reactant side, on the left-hand side, and my carbon source for product, carbon dioxide, comes in units of single carbons, I'm going to have to multiply by the stoichiometric coefficient of 18 to get the 18 carbon atoms that I need to balance carbon on both sides of the equation. Well, we should note by putting a stoichiometric coefficient of 18 in front of carbon dioxide, we're multiplying the number of oxygen atoms 18 times 2 to give us 36 oxygen atoms now as products with carbon dioxide. If we take a look at hydrogen on the left-hand side of the equation, we have 36 hydrogen atoms. On the right-hand side of the equation, the only product that we have that contains hydrogen is water. If we need 36 hydrogen atoms and they come in units of 2 in H2O, then what we need is we need 18 water molecules, a stoichiometric coefficient of 18 in front of water, to give us the 36 hydrogen atoms that we need to balance hydrogen on both sides of this equation. Again, because water contains both hydrogen and oxygen, we are also multiplying our oxygens by 18 on the product side. All right, so if we look at what we've balanced so far, we see carbon and hydrogen are balanced on both sides of the equation. What we need to do now is play with the stoichiometric coefficient in front of O2 to balance out our oxygens. Well, the first thing that we're going to do on the product side is we're going to take a look at our two sources of oxygen, carbon dioxide and water. We're going to add those oxygen atoms together, and we'll see that that ends up to be 54. Well, on the reactant side, we have two sources of oxygen. We have stearic acid, which will give us 2, and then we have our O2 molecules. Well, we would rather not have to play around with the stoichiometric coefficient in front of stearic acid because that will change carbon and hydrogen and we'll have to start all over again. So what we will do is we will assume that the stoichiometric coefficient in front of stearic acid remains 1, which means of those 54 oxygen atoms as products, 2 of them will have originated from stearic acid. If we go ahead and do the math on that, we see that we've got a requirement for 52 more oxygen atoms on the reactant side. Our only other source of oxygen is O2. Since O2 comes in units of 2, if I'm going to use oxygen molecules to provide those other 52 oxygen atoms, I'm going to have to divide by 2. And when I do that, I see that I end up needing 26 oxygen molecules, O2, to balance out my chemical reaction. Now, if we go ahead and take a look at all of our carbons, we've got 18 on both sides of the chemical equation. If we look at our hydrogens, we've got 36 on both sides of our chemical equation. For oxygens on the reactant side, we have 52 from O2. We have 2 from our stearic acid molecule for a total of 54. And if we add up the oxygens on the other side of our chemical equation, we see we have 54 on that side too. Our chemical equation is balanced.